Hi, everyone. My name's Bibbit. I'm here to present at the Differentiable Physics for Robotics workshop at RSS 2022. And I'm going to present on if we can apply differentiable simulation in low data regimes. Let's first consider the problem of asking your future home robot to perform a task for you. It's going to be clear that they will need to make sense of their surroundings, make and break contact with new objects with precision where needed, and quickly. Because if you ask your robot for a glass of water, you probably want it today and not next week. So building a model on the fly can actually be quite challenging, specifically if the data is ridden with impacts, such as what arises through frictional contact. As we can see here, doing this in a black box sort of way is actually quite challenging, and models can predict outputs that are highly unrealistic. Like, for example, this cube predicted being wedged partway into the table and landing on a corner instead of a face. In our lab, we showed through contact nets that we can combine analytical and data-driven approaches with a novel implicit loss function that can perform much more realistic predictions, such as those depicted on the right. Well, particularly in low data regimes when compared to end-to-end or other approaches. To learn exactly what that is, let's start from scratch. So in the model building process, we could think of a model as like an explicit model where the inputs are the state and perhaps any control input, and we directly learn what the next state should be. So this is learning a physics engine in a black box way. And a straightforward way to train this learned block is to just do backpropagation through the entire pipeline, so differentiate through the simulation. There are some obvious reasons that explicit methods struggle, namely, they have to learn some pretty intuitive physical facts about how the world works from scratch. So it might be reasonable to embed in some knowledge of this. And one way to do this is with an implicit method that can incorporate an optimization problem that's parametrized by physical quantities that you could learn. And this might look like a weird setup here, but this is actually what's under the hood in many of your everyday simulators, such as Mujoko, Drake, and Bullet, as well as others. A straightforward way to train this learned block is to, again, just perform backpropagation through the whole chain, including through the optimization problem. So what can we say about how the two of these approaches generalize? So in our L for DC paper, we were able to show that the generalization error bounds for an approach looks like this relationship. So there are a lot of numbers and symbols in here, but some of the relevant parameters that can be the same across approaches given a parametrization of the problem are these. So K is the number of learned parameters, delta is some failure probability that this generalization error bound holds. And we note that the data set size appears in the denominator here. So for any approach, if you have infinite data, really all of them will generalize well. And that's why we're particularly interested in cases where this n is small. So all of these terms make a difference. The important differentiating value here is actually this Lipschitz constant of the loss function with respect to the learned parameters, theta. And this is the quantity that ends up making the biggest difference between these approaches. So let's go into what this might look like in an example. Let's use a one-dimensional toy problem of a point mass that is falling under gravity and can collide inelastically with a flat ground whose height we are trying to learn. So here the theta is just one value, the height of this ground. And we can show that the loss-Lipschitz function value with respect to the learned parameters for the explicit loss actually scales with 1 over the time step of your simulation. So that means the finer resolution your simulator, the worse it will generalize. And maybe surprisingly, the differentiable simulation method provably performs the same when the theta represents the same value. This might be a little more obvious mathematically. So if we look at the loss formulations, an explicit formulation here looks like just the prediction loss. So the difference between the true output y and the predicted output f of x, and just square the norm of that distance. And here, remember that this function f is stiff with contact. That's the data we're interested in. In contrast, here's what differentiable simulation looks like, where instead of learning f explicitly, we learn a function g, where g depends not only on the input data x, but also on an optimization variable lambda, which is solved to be the minimizer of the constraint equation h. And really, we can just note that everything here in blue is exactly equivalent to f. So there's no surprise here that actually when theta represents the same values, there's no difference between these approaches. So how can we do better? If we look back at the approaches that we already tried, here's what ours looks like instead. We will notice that first we formulate a different kind of optimization problem that not only takes in the current state and physical parameters, but also takes in the true next state. And it looks at the transition between state 1 and state 2, finds the contact forces that best explains that transition, and then we penalize those predicted contact forces based on how realistic they are given the physical parameters we believe are true of our system. Then we can perform backpropagation on that value and update our learned block that way. Returning back to our toy problem, we can show that this loss-Lipschitz function with respect to the parameters theta is completely independent of the time step. So this poor scaling that we see for explicit and diff-sim approaches is entirely eliminated when we perform our approach. Going back to the loss formulations, our violation implicit loss instead looks like this, where lambda no longer strictly minimizes h, but lambda is chosen to minimize the sum of both the prediction term and the physical realism, so violation of the learned function h. And one reason why this might intuitively be a good idea is that, remember, this h constraint function is also being learned because it depends on theta. So it might not make sense to strictly look at the manifold that satisfies minimizing h, especially early on in the training process, where that h might not match your true system anyway. We can discuss a couple of examples for where differentiable simulation approaches struggle. And one of those is that the loss gradients with respect to contact parameters, so geometry and friction, is 0 anytime contact is not predicted. And that can be a problem if we initialize our geometry to something that's too small, such that the predicted next state doesn't see any contact, but the true next state does. There's no way for, in a differentiable simulation approach, given a stiff simulator, for us to learn anything from this 0 gradient in this scenario. So it will never learn to expand the geometry in this case. Another example is the gradient, again, with respect to friction, goes to 0 with worse and worse overestimate. So if we estimate that the friction parameter is too large, such that we predict zero velocity for the next state, but the true velocity isn't zero, then that loss gradient also goes to zero. Now, we can note here that plenty of differentiable simulators get around these issues by artificially softening the contact dynamics, which can work in giving informative gradients, but again, just means that the simulation is less accurate to what we would see in real life, where contact truly can be quite stiff. We note that our approach doesn't do this, and we, instead of smoothing the contact dynamics, we smoothen the loss itself. So if we drive our loss to zero, we can both uphold perfect rigidity and stiffness in contact, as well as learn any of the physical parameters that we're trying to optimize for in our physical model. So let's see what the results can be between these approaches on an example. So here we use the cube toss data set from the Contact Nets paper, where a three-dimensional real-life cube is tossed and collides with and tumbles on a flat table. And we're trying to learn things like its geometry and its friction. We will try both differentiable simulation approaches as well as our contact nets approach, and we will train for just 10 epochs on various small numbers of tosses, so low data regime. And we'll try two different scenarios. First, where we initialize our learned values to be too small, we'll denote that by S. And second, where we initialize those values to be too large, denoted by L. So here's what that geometry learning looks like, where we note that the true dimension is undetectable for differentiable simulation if no contact is predicted, as we discussed earlier. So that can be shown here by this line down here, where the predicted value was predicted to be too small. So true value is 1, and it starts at something like 0.45. And no matter how many tosses we see, differentiable simulation cannot learn that it needs to go to a higher parameter. This is because, like we discussed, the loss gradient is completely uninformative. We also note that no matter how many, whether we start too large or too small, and no matter if we start with only 2, 4, 8, or 16 training tosses, Contact Nets is able to successfully recover these values basically perfectly every single time. And even for the case where we initialize too large, the differentiable simulation approach sees a much wider band of confidence intervals, especially at the low training toss numbers. So just to look at some next steps here is we really want to increase our data efficiency even further. So just to explain where we currently are here is at ICRA just a couple months ago, we were able to perform live demonstrations where at just around 10 or 20 tosses, we could show perfectly reasonable convergence of the learned geometry of our cube. But we want to go even further than this, and we are thinking about leveraging vision so that we could abandon our April tag usage right now and supervise some of this geometry learning from our camera data directly. And maybe we could improve this data efficiency by an order of magnitude. Also, there might be some other smart tricks that differentiable simulators are doing to start to avoid some of these problems that we pointed out here. So it would be important for us to explore other existing differentiable simulators and how they handle these scenarios. With that, I'd like to thank my collaborators, Matt Halm, Nikolai Matney, and Michael Poza. And I thank everyone for your time and listening to our presentation.